This is a cheetah, popular for its speed, which can reach up to 120 kilometers per hour. Although it doesn't know it yet, it is about to revolutionize how we build robots. Why? I'll explain. Because this is absolutely embarrassing. And that revolution is happening right here in Africa. You see, right now, it has inspired three different robot prototypes. One of them is Dima, which is a wheeled robot with aerodynamic tail. Baleka, which is Africa's first bipedal robot. And Kemba, which is a pneumatic powered quadruped. I'll go into details on all of this in just a moment. But you see, each of these robots uses different aspects of a cheetah inspired movement mechanics. So let's get right into it. You see, a feature that makes humans different from other animals is our ability to stand upright. It might seem like no big deal, but look around you. Nothing else walks like us or keeps its balance like us. Humans can jump, roll, run, sometimes even while bearing load, without tipping over most of the time. And that's a very hard detail to replicate in robots. Right now, the AI race is in full swing, and labs around the world are putting blood, sweat, and tears into developing robots that can do so much more than just generate text. They want robots that can clean the house, robots that can walk your pets, be a security guard, be a combat fighter, or even in very extreme cases, be an athlete. However, we still need a few key details to perfect this robot obsession. And that detail is balance. How do we build robots that can carry out a wide range of motion without falling over? That's the question that researchers at the African Robotics Unit at the University of Cape Town are trying to answer. And for this answer, they've been studying the cheetah for clues, specifically its tail and fur. And here's what they found. When a cheetah is on the run and needs to maintain agility, the fur, it turns out, creates drag. At a top speed of 120 kilometers per hour, even lightweight fur becomes an aerodynamic rudder, stabilizing the cheetah's body through turns that would send most animals tumbling. How do they know this? Because they tracked the animal, but not in the way traditional motion trackers do. Traditional motion capture fails when your subject accelerates from 0 to 100 kilometers per hour in 3 seconds. The biomechanics equipment designed for human athletes in controlled labs becomes useless when confronted with a hunting cheetah. Because you see, standard systems require markers attached to the body, controlled lighting, and other subjects, or at least subjects that stay within a confined space. None of these conditions exist on the African savanna. And so the African Robotics Unit built their own system from scratch. They combined something called LiDAR with telescopic lenses to create long range motion capture that works from distances where the cheetahs don't even know they are being studied. The setup tracks the full skeleton in motion, every joint, every subtle adjustment as the animal hunts across open terrain. This groundbreaking motion capture technology is now a subject of interest outside the University of Cape Town's robotics lab. Sports scientists have expressed interest in using similar systems to study athletes in actual competition rather than laboratory simulations, which we currently do. Wildlife veterinarians see potential for monitoring animal health without capture or sedation. The technology could track everything from a limping elephants to the gait changes that signal disease in antelope populations. So, I mean, it's exciting to see what can happen next. But now let's talk about the three robot developments that have been inspired by the cheetah's tail and fur. The Cape Town team has built 3 robots. I spoke about that earlier, based on their cheetah research, with each addressing a different challenge in robotic movements. The first one, Dima, rolls on wheels but uses a tail for high speed turns, testing whether aerodynamic control beats inertial systems in practical applications. The robot's tail adjusts its angle to create variable drag, allowing it to corner at speeds that would typically require much heavier stabilization systems. And then the next one is Baleka, which became Africa's first bipedal robot, engineered to jump higher than any human by applying cheetah-derived principles to two-legged locomotion. You see, while a cheetah runs on 4 legs, the explosive push-up mechanics translate surprisingly well to bipedal jumping. The robot Baleka stores energy in spring-loaded joints, then releases it in coordinated bursts that mimic the cheetah's acceleration pattern. And the third one, Kemba, takes the most radical approach. Using pneumatic pistons instead of traditional motors, Kemba does the same thing: explosive power over precise control. The robot's legs fire like pistons in an engine, each push calibrated for maximum force rather than careful placements. The team modeled Kemba's pneumatic knees using something called Simscape Multibody and Simulink, developing controllers that mimic the cheetah's burst force approach to movements. Where most quadruped robots prioritize balance and foot placement, Kemba prioritizes raw speed and recovery. If it stumbles, it doesn't try to prevent the fall. It uses the momentum to spring back up, just like a cheetah recovering from a missed turn. According to the researchers, cheetahs don't try to finely control their feet. They just push off as hard as they can. So, what does this mean for the future of robots development? The team's next challenge involves cracking the cheetah's decision-making code. At the moment, they can measure every movement, calculate every force, but they still don't fully understand what the animal prioritizes moment to moment during a hunt. At the moment, there are still more questions than answers. Questions like, is the cat trying to conserve energy when running? Or is it trying to increase maneuverability or intercept prey in the shortest time? The answer changes everything about how robots should move. If energy conservation dominates, then maybe robots should glide between bursts of activity. If maneuverability matters most to the cheetah, then maybe robots should maintain readiness for instant direction changes. If time to intercept the prey drives the cheetah's decisions, the optimal strategy involves calculating risks and occasional spectacular failures. And in that case, that will be fine. So the team is now using something called inverse reinforcement learning, essentially running their equations backward to understand what objective function evolution has programmed into the cheetah's neural circuits. So what they're doing is they feed the motion or the motion capture data into machine learning algorithms that try thousands of different optimization strategies until they find one that produces cheetah-like movement patterns. It's absolutely mind-blowing. And I'm excited for what they're going to do. And to be honest, it is stories like this that keep me in love with Africa. And if you're excited about being in love with African stories as well, then maybe you have found the right channel for you. So, subscribe. I'll see you in the next video.